Welcome to ShowOffer.io, where we're here to help you uplevel your interview performance and land your dream offer from top tech companies. My name is Tony, and I'm a technical coach on the ShowOffer platform. At ShowOffer, we specialize in helping candidates navigate the most critical parts of the interview process, from breaking down complex system design problems to prepping for behavioral questions and even spotting red flags that could result in a rejection or lowball offer. We also offer insightful coaching sessions, live mock interviews, and personalized feedback, all aimed at making you a more confident, structured, and hireable engineer. Today, I'll walk you through one of the most frequently asked system design questions in 2025 for YouTube and Uber. That question is, how to design a top K system. Before we explore architecture or optimizations, we need to understand what this system is fundamentally responsible for, both functionally and operationally. Let's begin with the functional requirements. The key product features this system must support. There are three core functional requirements. 1. Retrieve the top K most popular videos. 2. Filter results by geographic location. 3. Support queries over arbitrary time windows. These three capabilities define what this system delivers to users and internal clients, whether for a trending tab, a personalized feed, or a regional analytics dashboard. In this problem, we use YouTube's Top K video ranking system as an example. Similarly, you can apply Top K to proximity for Uber drivers in dispatch process. The core idea is similar. Let's take the first requirement. The system must be able to return the top K most popular videos based on a defined ranking metric, such as view count, engagement score, or watch time. This is the primary goal, to continuously process massive volumes of user activity and surface the most relevant content in real time. This enables dynamic features like YouTube's trending page or TikTok's recommendation feed. It also introduces the challenge of fast, scalable, and continuous ranking over an extremely high cardinality space. Second, the system should support filtering top K queries by location, like top videos in the US or top 10 in India. This adds an important layer of personalization and regional relevance. It also reflects real-world differences in viewing behavior and content popularity. From a system perspective, this means tracking popularity separately for each region, increasing both storage complexity and aggregation dimensionality. Third, users should be able to define arbitrary time windows, like show me top videos from June 1st to June 7th, or even between 10 a.m. and 3:15 p.m. yesterday. This flexibility is essential for use cases like time series trend analysis, campaign monitoring, flash events, and retrospective reporting. To support this, the system must process data in fine-grained buckets and enable fast aggregation across any time span, even across hundreds of intervals. That covers what the system must do. Now let's focus on what the system must handle: the performance, scale, and accuracy constraints that define how the system needs to behave. But before that, we need to discuss a key trade-off, that is, exact versus approximate accuracy. If you're building a leaderboard, where fairness, payouts, or competitive positioning depend on precision, you'll need exact accuracy, using techniques like distributed heaps and full sorting. This requires high memory and coordination, and adds significant engineering complexity. But for real-time discovery features, like YouTube trending, approximate methods offer a far better trade-off. By using structures like count min sketch or heavy hitters, we can deliver fast, scalable, and cost-efficient rankings with only minimal accuracy loss. Because these two directions lead to fundamentally different system architectures, we've prepared a separate write-up and video focused on leaderboard design, available now at ShowOffer.io. For this walkthrough, we'll assume we're optimizing for approximate real-time top K, which gives us more flexibility and performance headroom. This is a common pitfall for candidates without clarifying the high-level alignment during their interviews. Assuming exact accuracy is always necessary can lead to over-engineered and inefficient systems. After alignment during your interview with your interviewers, you may come to the non-functional requirements for our system. 1. Low latency. Query responses should return within 10 seconds, ideally much faster for common regions and recent time windows. Second, high scalability. Ingestion pipeline must handle 5 million events per second, distributed across 10 billion video IDs. 3. Approximate precision. Target 1% error on frequency estimates, with at least 95% accuracy for top K results. 5. Cost efficiency. Use less than 1 megabyte of memory per stream, leveraging compact approximate counters. 5th, data freshness. Keep top K results up to date every 30 to 60 seconds, supporting near real-time relevance. These constraints will shape everything in the system, from how we partition data, to which counting structures we use, to how queries are executed across time and region dimensions. Next, we'll explore the data flow stages that connect ingestion, aggregation, and querying, and see how each stage aligns with the system's functional goals and performance targets. Let's dive in. Now that we've covered what the system needs to do, let's walk through how it processes data end to end. We'll break this into 4 core stages, from raw video activity to ranked queryable results. Each stage serves a specific purpose and can be independently scaled or optimized. This modular structure is key to handling real-time updates at massive scale. Stage 1 is event ingestion. This is where raw user activity, like video views, likes, or shares, is ingested from client logs or event buses. The system parses and cleans each event, extracting just the essential dimensions: video ID, timestamp, and location. The result is a structured, high-volume stream of simplified events, optimized for downstream processing. Stage 2 is pre-aggregation and counting. This is where we track how popular each video is, not globally, but within specific partitions, by location and time window. To do this efficiently, we use approximate counting structures like count-min-sketch or heavy hitters, we will cover later. These keep memory usage low while still producing reliable frequency estimates. The output is a live stream of partial counts, structured, compact, and continuously updated. Stage 3 is top K materialization. Once we have approximate counts for each region and time window, we compute the actual top K list, say the top 10 videos in India at 3:15 p.m. These pre-computed lists are stored in fast-access storage like Redis or a key-value store. This stage allows us to cache hot results and serve them quickly, without recomputing rankings on the fly. Stage 4 is the serving layer. Here, external services, like the homepage feed or analytics dashboard, can query the system by region and time window. The query engine pulls the relevant top K lists from storage, optionally merges across time slices, and returns the final sorted results. This is what ultimately powers your trending tab, recommendation surfaces, or reporting endpoints. Together, these 4 stages, ingestion, counting, materialization, and serving, form the backbone of the system. Next, we'll explore how these pieces fit into a high-level design architecture. Let's walk through how this system fulfills the 3 core functional requirements, starting with real-time ranking of popular videos. Here is the high-level design diagram. The process begins with raw user activity logs, such as video views and likes, coming from clients like mobile apps or web browsers. These logs are either archived in S3 or streamed in real time to Kafka, our message broker. Each Kafka event contains metadata like the event type, video ID, user ID, timestamp, location, and device. But for ranking, we only need a few essential fields. In the ingestion layer, these events are transformed into a lightweight structure. video ID, location, event time, rounded to the minute, and a score of 1. These transformed events are pushed to a Flink stream processor. This is where functional requirement 1 is addressed, retrieving the top K most popular videos by view count. Flink groups events by video ID, location, and minute, and uses an in-memory hash map to count occurrences. Once per minute for each region, Flink sorts these counts and emits the top K list. This results in a structured snapshot of trending content for every region, every minute, which is then written to a key value store like Redis. That leads us to functional requirement 2, filtering by geographic location. Since every event carries a location field from the beginning, and we group and store data using that location, the system naturally partitions popularity by region. Each top K record is stored under a composite key. This makes it trivial for clients or downstream systems to fetch region-specific trends without needing any extra filtering logic. Each of these top K records in Redis stores a list of the most popular videos for that specific minute and region. The values might look like video ABC 123 with 1205 views, video XYZ 456 with 1182, and so on. Now let's turn to functional requirement 3, supporting arbitrary time window queries. Because we store results at minute-level granularity, we can dynamically compose top K answers over any time range. When a user asks for the top videos over the past 24 hours, the trend query layer simply pulls all minute-level top K records for that region, aggregates the counts, resorts them, and returns a final top K list across the entire window. This gives us maximum flexibility. Users can query for 5 minutes, 6 hours, or an entire week, all using the same underlying data model. And because the data is already pre-aggregated into minute buckets, query latency remains low. Finally, the client application, whether it's a web dashboard, mobile app, or internal tool, makes a call to the feed or UI layer. That layer connects to the trend query layer, which returns the final ranked result, the most popular videos for a given region and time span. While this design works well for small to moderate scale, it quickly breaks down under real-world traffic. As the number of users, videos, and regions grows, maintaining exact in-memory counters for every video ID, location, minute combination becomes unsustainable, leading to high memory pressure, slower aggregation, and eventual performance bottlenecks in the stream processor. Additionally, querying across long-time windows involves merging thousands of per-minute top K lists, which can introduce latency spikes and excessive compute. To address these challenges and make the system production ready, we need to re-examine the core bottlenecks, and that's where our deep dive begins. Let's take a deeper look at one of the biggest scaling challenges in our top K system, counting video views at global scale. On the surface, it sounds simple. Track how many times each video is viewed, and rank them. But when you break this down by region and time window, the math gets overwhelming fast. Let's say you're processing view data for 10 million active videos across 200 regions. You also track counts on a per-minute basis. That's 10 million times 200, giving us 2 billion unique video ID, location, minute counters, and that's just for a single minute of data. Now assume each in-memory counter uses 40 bytes, including keys, values, and metadata. That's 80 gigabytes of RAM per minute. Over 1 hour, you're looking at 4.8 terabytes of state just for view counts. And here's the kicker. Most of those videos are long-tail content with only a few views, so you're burning through terabytes of memory to store mostly noise. As your platform grows, this naive approach quickly becomes the bottleneck. You hit limits in memory usage, garbage collection, and state checkpointing, and your stream processors simply can't keep up. So what's the fix? We turn to approximate counting, and specifically, a structure called count-min sketch, or CMS. Count-min sketch is a compact, probabilistic data structure that allows you to estimate item frequencies with bounded error and fixed memory size, no matter how many unique IDs you see. Here's how it works. Imagine a two-dimensional array with, say, 3 rows and 10,000 columns per row. Each row uses a different hash function. When a new event arrives, for example, a user watches video ID equals a BC123, we hash that ID into each row. H1 maps it to column 12. H2 maps it to column 385. H3 maps it to column 17. Then we increment the cell at each of those positions. This takes constant time and doesn't store the video ID itself, just bumps integer counters. Later, if we want to estimate how many times ABC123 has been viewed, we hash it again through all 3 hash functions and look up the same cells. Let's say we get 10, 11, and 13. We return the minimum of those values, in this case 10, as our estimated view count. Why the minimum? Because hash collisions can only inflate a count, never deflate it. So the mine gives us a safe upper bound. Now let's compare this to the original memory-heavy design. Exact counting required 80 gigabytes per minute. With CMS, a single sketch with 5 rows and 10,000 columns uses only 200 kilobytes. Across 200 regions, that's 40 megabytes per minute, or just 2.4 gigabytes per hour. A 2,000 times reduction in memory usage. This shift from exact to approximate unlocks scalability. You go from terabytes of pressure to something you can run comfortably in memory, all with 1% error. But CMS has one major limitation. It doesn't store keys, because you can ask, what's the count for video ABC123? And CMS will answer with a good estimate. But you can't ask, which videos are the top 10 right now? CMS doesn't know what items it has seen, just which counters it's incremented. And that's a problem, because top K queries aren't just about frequency estimates. They require identifying which video IDs are the most popular. To solve this, we pair CMS with a heavy hitters tracker, or HH. A heavy hitters tracker, often implemented using the space-saving algorithm, keeps a small, fixed-size list of the top items seen in the stream. It explicitly stores video IDs and their approximate counts. Here's how it works. Every event updates both CMS and the heavy hitters list. If the video is already in the list, we increment its count. If it's not, and the list is full, we evict the item with the lowest count and insert the new one, using the CMS estimate to set its minimum possible frequency. This hybrid approach gives us the compactness of CMS and the queryability of a heap. CMS gives us fast, space-efficient frequency estimation for all items. Heavy hitters keeps track of the actual top N items, video IDs and all. Let's say CMS is tracking 10 million videos with 1% error, and your heavy hitters tracker holds the top 100. Now at any moment you can answer, how many views does ABC123 have? Where CMS handles that. What are the top 10 trending videos in the US right now? Where HH gives you that instantly. Together, CMS and HH give us real-time, memory-efficient, and accurate enough rankings, suitable for any user-facing experience where perfect accuracy isn't required. It's a dramatic improvement over exact counting, and it lets us process tens of millions of events per second across billions of IDs, all while staying performant and cost-efficient. Of course, for use cases like leaderboards, audits, or payouts, where even a 1% ranking error isn't acceptable, this approximation isn't enough. But for real-time discovery and trend surfacing, it's ideal. Now let's tie this back to how the architecture changes after applying these optimizations, as shown in the updated Deep Dive 1 diagram. First, stream ingestion remains the same. User activity events are pushed into Kafka. Then, in the stream processing layer, now powered by Flink, we compute view scores, partition by location, and aggregate within windowed intervals. Here's where the new logic kicks in. Instead of maintaining billions of individual counters, we maintain a CMS sketch and optional heavy hitters tracker per region time window. These structures are small, memory efficient, and designed to emit approximate counts as output, not raw event logs. That approximate count stream feeds into the top K materializer, which flushes compact top K lists into a fast key value store like Redis, organized by region and time window. And if we ever need to recompute or reconcile with ground truth, we have an optional offline audit pipeline. All raw logs are persisted to S3. The offline audit processor can pull this data, compute exact rankings offline, and patch discrepancies in the top K store, ensuring downstream systems like billing or creator rewards receive accurate data when needed. This design unlocks a massive jump in scalability, while still preserving correctness guarantees for critical workflows. In our next deep dive, we'll look at how to support arbitrary time windows, and how to structure time bucketing and retrieval logic to make real-time top K queries both flexible and efficient. One of the most powerful user-facing features of a top K ranking system is the ability to query across arbitrary time windows, like, show me the top 10 trending videos in the US from 6 p.m. to 6:45 p.m. It sounds simple, but supporting these flexible queries at scale, across billions of events per day, introduces a classic system design challenge. How do we structure time in the system to keep ingestion efficient and queries fast without exploding storage or memory usage? There are three primary strategies used in large-scale time-windowed aggregation systems: tumbling windows, sliding windows, and event time bucketing. Each has trade-offs across ingestion complexity, query flexibility, and memory efficiency. Let's walk through them. The first approach is tumbling windows. Tumbling windows divide the timeline into fixed, non-overlapping intervals, for example, every 15 minutes. Each event falls into exactly one window. The system aggregates data per window and stores one result per period. This is simple and efficient. It minimizes storage, keeps ingestion lightweight, and makes querying fast, since all relevant data is pre-computed. But there's a major limitation: lack of flexibility. If a user asks for data from 6:10 to 6:45 p.m. and your tumbling windows are aligned at 15-minute marks, you're stuck. You can't serve that query exactly unless you reprocess raw data or give a partially incorrect answer. This makes tumbling windows great for dashboards, but poor for user-driven queries. The second approach is sliding windows. Here, windows overlap and move forward in time at regular steps, like a 15-minute window that advances every 5 minutes. This gives you more freshness and smoother trend tracking. But it also introduces redundancy. The same event can contribute to multiple overlapping windows. For real-time stream processing, this means more state to manage, more frequent updates, and more compute. Sliding windows are useful when you want to track rolling statistics, like the moving average of views over the past hour. But they're expensive to maintain and still don't support truly arbitrary start and end times. The third strategy, and the one we use in this system, is event time bucketing. Instead of assigning events to fixed windows, we bucket them by event timestamp, usually at a fine granularity like 1 minute. Each bucket contains data only for its specific minute, and all buckets are stored in sorted order. This has three huge advantages. Flexibility. We can dynamically compose any time window by selecting the relevant minute buckets. Want data from 6:07 to 6:042? We just fetch and merge those 36 buckets. Simplicity. Each event contributes to exactly one bucket. No overlap, no redundancy, no duplicate state updates. Efficiency. We don't pre-compute every possible window. Instead, we maintain small, non-overlapping units that can be combined on demand. Of the three strategies, Event time bucketing is the only one that balances flexibility and scalability, which is why we use it. Let's walk through how the three main windowing strategies compare: tumbling windows, sliding windows, and event time bucketing, across 5 key system properties. First, can they support arbitrary time windows? Tumbling windows are rigid. They only support queries that align exactly with their fixed intervals. So, no. Sliding windows are a bit better, but still limited by fixed step sizes. Limited support. Event time bucketing? Absolutely. It offers full flexibility to compose any custom time range at query time. Next, ingestion complexity. Tumbling windows shine here. Very low complexity with no overlaps. Sliding windows, on the other hand, require frequent overlapping updates. High complexity. Event time bucketing sits in the middle. Moderate complexity. You handle one bucket per event, but there's no redundancy. Now query efficiency. Tumbling windows are fast. Results are pre-computed and ready to serve. Sliding windows? They're expensive to query due to overlaps and multiple partial windows. Event time bucketing is slower. It requires fetching and merging multiple small buckets at query time, especially for long ranges. Fourth, memory efficiency. Tumbling windows are great. Each event belongs to only one window. Sliding windows again struggle, storing redundant states for overlapping windows. Event time bucketing? It's clean and flat. One bucket per timestamp with no duplication. Finally, flexibility. Tumbling windows offer poor adaptability. You're locked into fixed intervals. Sliding windows provide moderate flexibility. Event time bucketing leads the pack. Excellent flexibility to serve any time-based use case, from microbursts to multi-day trends. So in the end, event time bucketing gives us the best balance of flexibility and scalability, especially when paired with a smart query engine that merges efficiently. But now we face a new challenge: query performance. In this model, data is spread across many small buckets. One per minute. If a user asks for a 3-hour window, we have to fetch and merge 180 different sketches. Multiply that across hundreds of regions or thousands of concurrent users, and the query engine starts to feel the pressure. Each minute-level sketch stores partial counts for many video IDs. So at query time, we need to fetch all matching buckets, aggregate scores per video ID, and sort and return the top K list. If we do this naively, scanning and merging linearly, we burn unnecessary memory and compute. This quickly degrades latency, especially on longer queries or under high QPS. To fix this, we apply a classic optimization, the two-pointer technique. Since all time buckets are stored in sorted order, we can perform a bounded scan. One pointer moves forward from the query's start time, the other from the end time, backward. These pointers define the exact slice of time we need to examine. We avoid scanning buckets outside the window and fetch only the necessary range. Once we've loaded that slice, say all top K sketches from 6 p.m. to 6:45 p.m., we aggregate the scores across time. For each video ID, we sum the counts. Then we sort the merged result and return the final top K list. This approach drastically reduces the memory footprint of the query and ensures latency stays low, even on wide-range queries. Let's now take a closer look at the updated system architecture after applying event time bucketing from Deep Dive 2. We'll walk through a real example shown in the diagram, highlighting the key changes. It all starts when a user watches a video in the US at 1842. This action emits a raw log event that flows into the stream ingestion layer, still handled by Kafka as before. Now comes the first change. In the stream processor, powered by Flink, we not only compute popularity scores and partition by location, but also assign each event to a specific time bucket. In this case, the video event is slotted into the bucket, Top K US 1842. representing views from the US in that exact minute. Next, we pass the event to the approximate counting layer, either CountMin Sketch or a heavy hitters tracker, depending on the implementation. Here, the corresponding sketch or counter for bucket 1842 is updated in memory. The system periodically flushes this in-memory state to a Redis cluster. Now let's fast forward to the query path. A user opens the trending tab and asks, "Show me the top K videos in the US from 1810 to 1845. The trend query layer kicks in. This layer uses a two-pointer strategy. One pointer locates the start of the range at 1810, and the other locates the end at 1845. Using this range, the query layer fetches the relevant 36 one-minute buckets from Redis. From top KUS 1810 to top KUS 1845. Each of these buckets contains approximate counts for that minute. The query engine then merges these partial counts, sums them up across the window, re-ranks them, and returns the final top K list to the UI. While the query engine does a bit more work, merging many small slices, the overall design remains scalable, flexible, and composable. Now let's come to potential deep dive 3. How to extend to strong accuracy without approximate. The design we've explored so far leverages approximate data structures like CountMin Sketch and heavy hitters to efficiently compute top K videos at scale. This strategy is well suited for real-time, user-facing use cases like YouTube trending, where high responsiveness, scalability, and acceptable precision, greater than or equal to 95% accuracy, are more important than exact counts. However, some systems, such as competitive leaderboards, financial reporting, or creator payout tracking, demand exact accuracy. In these scenarios, even small ranking errors are unacceptable, and approximate methods can't provide the guarantees required. To support strong accuracy, the architecture needs to shift significantly. Use exact counters rather than sketches. Maintain strict ordering and full ranking consistency. Often requires centralized coordination or precise aggregation, e.g., distributed heaps, mergeable sorted sets. These topics introduce additional trade-offs: increased memory, higher coordination cost, and more complex state management, all of which must be considered carefully in design. For a detailed exploration of how to design a system that supports top K with strong, exact accuracy, refer to our Another System Design article on leaderboard design. We'll cover distributed heaps, sorted aggregators, tie-break strategies, and how to reconcile real-time updates with ranking integrity. And that brings us to the end of our walkthrough. We started with a simple goal: build a system to rank the most popular videos in real time across regions and time ranges. Along the way, we tackled scaling bottlenecks, counting accuracy, and time window flexibility, all while balancing trade-offs in memory, performance, and correctness. Through 2 deep dives, we explored how CountMin Sketch and heavy hitters reduce memory cost without sacrificing visibility, and how event time bucketing enables arbitrary time window queries with low ingestion overhead. Together, these patterns form a robust foundation that can scale from prototypes to production at billion-user scale. Of course, there's more beneath the surface. Things like handling late data, ensuring data consistency across stream and batch, and surfacing explainable metrics to users. We'll cover these in future installments. If you're preparing for system design interviews at companies like Databricks, Meta, or OpenAI, or just want to build better back-end infrastructure, we hope this gave you the mental models and vocabulary to shine. Thanks for watching, and don't forget to check out the full write-up and more coaching material on ShowOffer.io.